somehow I missed my final comments, so just quickly redoing them. They didn't take long. So we've calculated the difference quotient for this function using this formula. We got this. Now for t equals 40 and h equals 40, we plug in and we get this, which is very, very close. Well, not very, but within tolerance. I said I'd be within a tenth. Thought I would, and I was. So this is negative 0.8, where the slope of this fundamental triangle is negative 0.7. So I make the statement that the difference quotient is the slope of the fundamental triangle on the interval from t to t plus h. Now why would I say that? Well, first of all, if t is 40 and h is 40, the interval from t to t plus h is from 40 to 40 plus 40, which is 40 to 80, which is this, right? The value of the function at t is f of t. So if my interval is from t to t plus h, the y-coordinate of this point is f of t. So this would be like my, let's see, what color could I use that I haven't used? I don't think I've ever use this. Actually, yeah. Okay. So this would be my t f of t. This point here that I should have pointed to is, well, the x-coordinate is your t plus h, the 40 plus 40, which is 80 in this case, but in general, it's t plus h. And the y-coordinate is what you get when you plug that into the function.
Yeah, I could go in there and get brisket.
So the coordinates of this point are t plus h, f of t plus h. Now, the rise from here to here is the change in the y-coordinate, which is this y-coordinate minus this. That's f of t plus h minus f of t, which is exactly what you have in the numerator of the difference quotient. And the run is from this point to this point. The x-coordinate goes from t to t plus h, so the run is, well, t plus h minus t is h, and very clearly the run is h. So there's our run. That's rise over run. So the difference quotient is the slope of the fundamental triangle. Now, I said I was going to show you some calculus, so I'm just going to briefly establish that. Okay? And I kind of need to do it just pointing here. If we do this over a shorter interval, like let t equal 40 and h equal 10, what would that look like? Well, if this is 40, 10 is about this much, so we would be doing a small fundamental triangle right here. The slope would be slightly different because this curve is concave upward. Okay, so the slope would be a little greater if you went to here. If you use the t equals 40 and h equals 10. If you use t equals 40 and h equals 1, it would be even just a little tiny bit steeper. And if you take the limit as h approaches 0, you get the actual instantaneous slope at this point. And that would be the slope of the line tangent to the curve at this point. Now we're going to talk more about that. I'm just giving you a preview. We're going to develop these ideas because I think many of you have a calculus course in your future. It's going to get you off to a good start if you remember what we're doing here. Also helps you learn all the stuff that we're doing in the pre-calculus. And pre-calculus traditionally includes a short introduction to calculus. So it's going to be very short. Okay, well, as h approaches 0, the slope approaches 0.02t.
Yeah, I want to check it.
Okay.
That's the only reason I'm trying to go to. What, if there's like a, there's an above 50.
Sorry, 0.02t minus 2. Okay, because the 0.01h goes to 0. Now the 0.02t for t equals 40 is 0.8 minus 0.2. The slope actually approaches negative 1.2. So the slope here is not as great, it's not as steep as it is here. It's actually fairly significantly steeper. It's negative 1.2 instead of negative 0.8. The expression you get when you let h approach 0, the limiting value of this as h approaches 0 is just, well, 0.02t minus 2. this is a formula
Have fun, no student.
for the instantaneous slope of this parabola
I'll give
at the
you
point
tips for tuition.
where the t-coordinate is t, okay? Point corresponding to t-coordinate t. It's the slope of the tangent line at that point. That's a great big deal. It's a huge deal.
Where they sacrifices when I did.
Now, we know that the slope of a fundamental triangle on an interval is also equal to the average rate of change of y with respect to t on the interval. As a matter of fact, that's how we chose to define the average rate of change. And we have been making sense of that idea. We'll continue to make sense of it. So we've associated the difference quotient with an average rate of change. The limit of the difference quotient is actually the instantaneous rate of change. And the difference quotient, as h approaches 0, approaches what we call the derivative of the function. And the derivative is a great, big, huge deal.
Y'all take it easy. All right.
The limit of the difference quotient as h approaches 0 is called the derivative. As I just said, the derivative is a formula for the instantaneous rate of change, how fast this function is changing at any instant. So if this function accurately describes the level of water in a container, the average rate of change is how fast the water is moving, how fast the surface of the water is descending in the case of the experiment that we did at that instant. Okay, now the next instant, t will have changed a little bit, and the rate of change will have changed. And it will have changed in a way that, well, we analyze later. Okay, so these are really important concepts, some of the most important concepts that Western civilization has ever stumbled upon. So it's a big deal. We're going to do a little bit with it to give you a context for a study of calculus.